My name is Ursula De Marco. I'm a research astrophysicist here at Macquarie University and a professor, and of course, like all of us here, I lecture students as well as do research. I work on stars. Many astronomers work on galaxies, very large structures. Some people work on planets, which are relatively small, and I do stars, which kind of smack in the middle. I particularly am interested when stars live and die in pairs or triples, so when they're in a little company. And that is because, just like in human life, a person can have a very rich and interesting life, but if that person is married or with a partner or with children or parents and lives in a group, that life is of course much richer and more interesting. So I just love studying these interactions and the way they shape the lives of stars. So one of my key questions, I guess one of the questions that defined my career and the way I work today, was looking at this nebula, a beautiful nebula. We observe them with fantastic telescopes, and they're really odd shapes. They're not just round, like stars are round, and the nebulae that come from them, one might expect, should be round. They are butterfly shapes, they have jets and all kinds of structure. And the question is, why do round stars produce such non-round nebulae? So about 10 years ago, I decided that I wanted to investigate the question of whether a companion star may have participated in the shaping of these interesting nebulosities. And so I decided, how do you go about asking this question and then giving it an answer? And the way that I felt was the best way was to write a computer model. Computers can really help us extend our brains and gaining complexity when our brain cannot really hold so many numbers, so many things together at the same time. And so I got into theoretical, actually numerical astrophysics, which is a subject that allows you to create models of complex systems. And in this case would be a star with a second star rotating around it and generating a kind of splashes of gas that then can contribute to these interesting shapes and morphologies of nebulae. The first thing you want to do when you have a question and you're kind of starting to think about how you would answer that, you need to take a look at what other people have done. Not just because if somebody else has done it, well done, it's done, or done, I don't have to ask that anymore. Usually what you find is other people have given partial answers to similar problems. And you can actually use their methods and their answers to help you kind of propel forward your own research. So the first thing I remember doing was, okay, who has written a computer model of similar problems? And indeed you find that, today you have so many researchers, so many papers already been written, you find that they're right there. Once I found that, I actually looked to see whether any of those researchers were known to me. They were friends or colleagues, or maybe they were colleagues of colleagues, friends of friends. And I found that one of my mentors, in fact in my own department at the time in New York City, was a good friend of one of the people who've written these papers. And I asked him to introduce me. So I started a collaboration with a person who had a similar question with some partial solutions, and that helped me to extend their work towards the direction I wanted to go to. In some cases, you develop your own tool from scratch, and in other cases, which is perhaps more common, you adopt somebody else's tool and you extend it, or you modify it, or you adapt it. And that's what I did. I am not the type of astrophysicist who can really develop a full code like this one from scratch, but there's so many around to play with. And fortunately, because in science we're really open, most people make their own codes available and they help you to use it and perhaps collaborate with you. And that's the best solution, because you really want a lot of eyes on these problems. It is easy to make mistakes. In the olden days, we had some data, but we didn't have a lot of data. So statistics was relatively useless, because if you have just one star and you're observing and you're looking at its colors and its size, it's not going to be statistics. Today we have phenomenal amounts of data. So we start looking at this data in unison, in their complexity. And statistics is absolutely necessary to draw the signal out. The answer is in there somewhere, but to draw it out, you really need to use these mathematical tools. Personally, in working in simulations, what I do get, what my byproduct is, big data sets where each point in my data set describes one little location in my star. And that little location is described as the density of the gas in that location and the temperature and these type of quantities, whether the gas is moving or not. And so I too need to use some statistical inference to understand whether within this mishmash of gas that is splashing in all directions, I have bulk motions. Is there a disk in there that's moving synchronously, or is it all expanding, or is it going in a chaotic manner? So in that sense, I too use statistics. In my case, more than statistics, what I need to figure out is whether the data that I get from my simulations is real, or is defined by the very computations that are being carried out to get the data. So can I trust the result of the simulations? This is a nice mathematical tool. There are procedures called validation and verification. In verification, we try to figure out whether the equations were solved correctly, for example. And there's lots of little test cases that you can do, simpler test cases. You can even sometimes do it on a piece of paper. It's like when you have a computer code giving you a number, what you should do is to check at least some of those numbers by hand, right? And then once few check out, then perhaps the others are good too. So that's one way. Validation in astronomy is often to do with observations. So some of my simulations give me some bulk properties. For example, this star, once it's interacted upon by this other star, is giving you a wind at this velocity. We have observations that show us those velocities. And so I can just figure out whether I'm in the ballpark. If I end up with very large values that make absolutely no sense, then I know I'm wrong. If I get velocities above the speed of light, well, that's a good check in physics. Nothing goes above the speed of light, so I know already that's wrong. So some I use just regular physics and my senses, and others I just look at observations of real astronomical objects. Publishing is very important in this industry, not just because somebody has decided that, but because if you don't tell people you're done, you might as well not do it, right? And after all, we are much of the money that pays for our research is from taxpayers, and so we need to account for what we do, right? And so we're all in agreement with that. Writing a paper is really hard. It's hard because you have to write coherently, you have to write engagingly, you have to have enough plots to show what you're talking about, but not too many and not too few, and they have to be the right type of plots. So there's a lot of complexity in that. And as I teach my students to write papers, I realize just how hard it is. By the time you're, in my career stage and at my age, you realize that you're kind of doing it as a second nature. And ultimately, it's really about telling a story. I believe that every paper, which is only a little bit of the research you'll ever produce, is itself a little story, a little book in a series, in a novel series, or a chapter in a book. So it has to have a beginning that says, well, guys, this is not the beginning of time. I'm starting from this, and there's some people who did some work before me that did these other things. So you connect it to the before. And then you have your little story, and the after is often, well, I get to this conclusion, and it's really interesting because, and you connect it to other fields. So for example, with my simulations, have been thinking about what happens to planets when stars become large and eat them up. And that is kind of interesting. People tend to pay attention, Stars will engulf many of their planets, oh yes, and we will be gone. In our case, 5 billion years, we got time. And so what happens to the planet? The planet gets destroyed. What happens to the star? Can the star be destroyed by a puny planet? Can we have the David and Goliath example? I like to engage my audience in such a way that they relate it potentially to what they're interested in. If it's a public audience, then we talk about life in the universe, we talk about planets being born, Earth's being somewhere in the universe aside from the solar system. If it is my colleagues, then they might be interested in, well, I have calculated a model for a planet being eaten into a star, but maybe you're interested in another star being eaten by a star. So they're very related questions, but you can start from what I've done. So we come full circle. I start from the work of my peers, and my peers can use my work for their own. There has never been a harder time than now to be a year 11 student, I think. It's really hard because the choices are many, and the mentors, the adults, are kind of a little bit at a loss too. Things are changing extremely rapidly. When I was a student, there was physics, and there was biology, and there was philosophy, and there was religious studies, or whatever. They were very compartmentalized, and you made a decision where to go, and then you just stuck with that. Today, there's no boundaries. Most of my astronomy students who do research, they do their PhDs, don't stay in astronomy. They go into data science and they use their analytical and computational skills in that. Some go in the movie industry because, the techniques we use are used to do animations. Others work for the car industry because the simulations I do also are the same simulations that people do in cars to understand hot exhaust fumes in the exhaust pipes of McLaren cars. So there's such an incredible wealth of stuff you can do with any one of the sciences that you think you're studying now. So it's not just that. And so if even astronomy can produce people who work for the car industry, can you imagine biology? You just name it. Every field of life is open to you. So the advice is continue doing what you like to do. If you have a passion, by all means, that is your biggest ticket in life. Stay passionate about that thing. If you don't have a passion, many kids today don't really know what they want to do. Some want to do many things and others just don't know. Well, continue on some path and it'll come to you. But no matter what, if you don't work really, really hard, nothing really comes. Work really hard towards a field that you've chosen. Work really hard towards finding what field it is that gives you that passion. Getting lukewarm grades, doing okay, is just not it. You need to really work incredibly hard, do very well, and things will start raining on you and come to you naturally.